Okay.
And we're starting. So we're going to pick up with Arclength. It's 8.1 Arclength. So last time we actually derived a formula. So let's say if y equals f of x is a differentiable function, because we want to be able to find its derivative at all points on an interval. And the length y from x equals a to x equals b is given by, now the typical variable used here is s, but I'm going to use L. The integral from a to b of 1 plus f prime of x squared dx. We sort of derived that using the distance formula before, and used Riemann sums to add up all these little distance formulas, and we ended up with that integral. So pretty much with these problems, it's just, you need to know, first of all, you need to have this formula memorized. It's just something we know now. So I'll give you the formulas for the approximate integrals topic, but I'm not going to give you this one. It's something that you're just expected to know. So in this situation, whenever you can write y as a function of x, it also works the other way, by the way. If you can write x as a function of y, you can do a dy integral. So that's one thing you can note as well. So if your function is like moving something like that, you want to figure out between, you want to figure out the length between c and d, given x equals some function of y and is differentiable. Then you can say L is equal to the integral from c up to d, from the lower y bound to the upper y bound of 1 plus f prime y squared y. Right, so it does work the other way as well. So you kind of do whichever one is convenient for you. There are times where you can actually solve for the other variable. So if you're given y equals a function of x, you can actually solve for x, because this integral might be easier to compute than that integral, and then whenever they can both work, you can use it. But in general, that's kind of the formula you want to take away from this, the square root of 1 plus the derivative squared. So let's actually just jump into some examples. Theoretically, there's really not much more to talk about. So find the length of y equals x cubed over 6 plus 1 over 2x on 2. So the first thing you'd realize is that this is differentiable. It is also differentiable on 1, 2, because all our functions are defined. X equals 0 would have been a problem, but we're not at 0, so it doesn't matter. And the phrasing can be slightly different, but it's essentially going to be the same question. Or instead of this guy, you could have said something like between x equals 1 and x equals 2. Or you could say something like from the point where x equals 1 to x equals 2. etc. Right? But the idea is they're going to ask to find the length of something on some interval where your function should be differentiable on that interval. If it's not differentiable on that interval, then you'd have to do something else, of course. But that's basically the idea. There are cases in which the curve might have sharp corners and you just break up the integral into pieces, but we're not going to worry about anything like that. So given that kind of question, you can just jump right into the formula. You don't even have to do an explanation. So what we're going to do is we're going to just find the derivative. What's the derivative? Do you remember how to do derivatives? What's the derivative?
1/2 x squared minus 2x to the negative 2.
Minus what?
2x to the negative 2.
ln 2 over 2.
Oh.
I mean, sorry, ln 2x over 2.
No.
It was half.
Like 1 over 2x is the same as 1
Oh,
half
yeah.
times 1 over x, which is 1/2 times x to the minus
1/2.
1.
Minus 1/2.
So that's your y, then your y prime would just be minus 1/2 x to the minus 2.
Yeah.
Okay? So this is basically 1 over 2x squared. So rewrite that through the power rule, and that's your derivative. And so what you're going to do now is you're going to find the derivative squared, which is going to be what?
X to the 4th over 4 minus 1 over 4 to the 4th.
No.
Oh. Oh.
Yeah, you just did a blasphemy there. It's a quick way to get a 0. You don't just square each term, you have to FOIL it, right? I know, Calc 2 is tough. You do all this like, oh my god, and then you come back there and I forgot how to walk. Do you differentiate 1 over x again? Oh yeah. Okay, so it's this squared. This times 2, which is ends up being minus a half, and then plus that squared. So it's 1 over 4x to the 4th. And so this means that the length of this integral is from 1 up to 2 of the square root of 1 plus this guy. Okay, now, how do you integrate that? Time to show off your integrating prowess. Ideas?
Maybe change it a little bit.
Okay, what would happen?
It'd just be 1/2.
So 1 minus a half is just 1/2, right?
Yeah.
Okay, how do you integrate that? Well, this one has a little trick to it. If you see it, do you see the trick?
Like, put all the exponents to 1/2, or,
What do you mean?
like, so you have 1/4 x to the 4th, and just, wait, never mind.
You know, like do this?
Yeah.
Oh, that's also wrong. That's a blasphemy as well. Right? You can't distribute powers across sums.
Can you, sorry, can
Yeah.
you multiply the denominator, like, multiply each term by like x to the 4?
You can't
Or
just
x to the
multiply by
fourth.
x to the 4th. You have to multiply and divide by x to the 4th. Yeah?
I think you can get a common denominator that u equal x to the 4th, and it should work, I think. Because then you'll cancel.
Probably, yeah, that would work out. There's something quicker though. I'll give you a hint. Compare this to that. What's the difference? Literally just the middle sign. I know this guy is that. What do you think this guy is?
Oh, it's just the plus.
It's just this guy with a plus sign instead of a minus sign. So this is just equal to 1 to 2 of this thing squared, which is x squared over 2 plus 1 over 2x squared. Now we're on an interval where the x's are positive, so the square root of something squared that's already positive is itself. Technically, I can just write it here as a technicality. Technically, you would get the absolute value here, but because our x is positive on this interval, it just ends up being itself. And so this we can integrate. That's x cubed over 6 plus this would be x to the minus 1 or minus. And so now I can plug in 2. Minus plug in 1. And I think that was 17. Now it turns out, the formula is very simple, but it turns out that this kind of formula, the radical of 1 plus y prime squared, you might not realize this, but this formula in practice tends to be actually very ugly. It's a very simple formula to write down, but when you actually apply it and plug in a derivative, usually you would end up with something very ugly. And so there are a lot of times in like the textbook where these problems will be like the problems where they said you can use a computer algebra system to solve, because the integral itself can be very messy. In the few instances where the integrals are something nice that we can solve, sometimes there are little tricks like this. There'll be some sort of relationship between these two that you can take advantage of. But in general, it will be hard to find a function that makes this expression a nice expression. It's usually going to be a very ugly integral, and so you might be asked to just set up the integral, not necessarily compute it. But if you're asked to compute it, it means there is a way to compute it, and you can look for a lot of little algebra tricks to really simplify before you go on down this road. And yeah, creating a common denominator, creating one big fraction, you'll get something that hopefully in the top you'll realize you can factor as a quadratic. But yeah. Did you have a question? Someone was raising.
No, I answered it myself, actually.
Oh.
Thank you.
So that's the idea. Let's get through these two really quickly. Find the length of y equals ln cosine of x. So that angle range is within the first quadrant, so the cosine is positive, so the ln is defined and differentiable. So yeah, so we're just going to use 1 plus y prime squared dx. Let's actually see what that ends up being. So if y equals ln of cosine, what is y prime? Right, minus sine x over cosine x, right? So the derivative of the thing over the thing itself, and so this is negative tangent x, which means that your y prime squared will be just tangent squared, which means that your length is going to be from 0 to pi over 4 of the square root of 1 plus tangent squared dx. How do you integrate that?
Secant squared. So
Yeah, that does become secant squared. There's an absolute value of secant, but secant is also positive on this interval. Because it's 1 over cosine, then the cosine is positive, so that's just this guy. Integral secant, anyone remember that?
is it secant x tan x? Or is it ln?
That's a derivative of secant.
ln cosine x?
No,
Sine.
it does involve an ln.
Sine. Oh.
Right, that was the weird one when you multiply and divide by secant plus tangent and you did the u sub. And so here we have ln of secant pi over 4 plus tangent of pi over 4 minus ln of secant 0 plus tangent of 0. Cosine of pi over 4 is 1 over radical 2, so if I take the secant, that is just radical 2. Tangent of pi over 4 is 1. This is ln of that. Minus secant of 0 is 1, tangent of 0, that's just ln of 1. Log of 1 is 0, so this can cancel. Okay?
You could make a function of y by just taking the square root of both sides. Like x equals.
Oh, okay. And our x is positive, so I know I take a positive square root, right?
Okay, yeah.
Yeah, because technically there's a plus or a minus, but I know that my x is positive, so it's going to be the positive square root, and so that would be y minus 1 to the 3 over 2.
Is
Well-
the integral 0, 8, x or y?
That's probably x, isn't
It's x.
Okay.
it? So then we need to find what it would be on y, right?
Okay, so you're thinking of this as a function of y. So we would need the y limits.
Wait, could we have done it the other way? Like solve for y? Or no?
Maybe let's do that. Let's try that after. See what that would look like. Shouldn't take too much time to do the other version. But let's keep running with this version and see where we get. So to find the y limits, you simply just plug in the x limits over there, right? So if you're if x equals 0, then that would mean that y minus 1 cubed equals 0, so that means your y is equal to 1. And if your x equals 8, this would mean that y minus 1 cubed is equal to 64, which is 8 squared. And so this would mean that y minus 1 is equal to, what's the cube root of 64? Is it 4? And so your y would be 3.
Wait, it doesn't have to be the 3/2 power. Y minus 1 to the 3/2 power. If x equals.
No, I'm using this version.
Oh, okay.
So I plug in the 8
Oh,
here,
okay.
8 squared is 64, and then,
Gotcha.
yeah, so y equals 3. And so here what I'm going to use is the limit, the length is going to be the length from 1 up to 3.
Is it 5?
5. There's this funny comic in God, no, it just slipped me. XKCD or something like that, what it's called. Do you guys know that comic, that online comic? You should, it's very funny. I'll probably send you guys a link to it. But it's a comic strip that some PhD student invented, so it's very like, very high-minded jokes, and they'll have all sorts of jokes. So it's like, so he'd like have a graph, like the more advanced math and the ability to do simple math. And then it's like it has this inverse relation. Like, yeah, when you're talking all this stuff, yeah, what's the cube root of 64? And like, yeah, I'm telling you, we're doing like some crazy math now, and you guys forgot how to differentiate one over x is the truth. Yeah. After a while, it's like the simple math is just like, it becomes hard for different reasons. It's kind of like you get so bored of it that your brain just shuts down on you. So x prime squared dy. So that's what I would use. But yeah, there's some nice jokes. It's a nice. There's another comic strip about this guy talking to another guy, and he says, I used to think that correlation implies causation, but then I took a statistics class and now I don't. And then the friend said, oh, so I guess it helped. And then he's like, maybe. Correlation means when two things happen together. Causation means one thing causes the other thing. So he's just saying, is it because you took the statistics class that now you understood this, or did those two things just happen together and you understood it for some other reason? That's where the joke lies. It's not it's the correlation versus causation. Anyway, so what do we have here? Did we actually differentiate this thing?
No.
No, let's actually do that. So x prime is equal to 0 to 2, y minus 1. You subtract 1, so that's going to be a half. Multiply by 1 because of the chain rule. And so if you took x prime squared, that's going to be 9 over 4 times y minus 1. And so this guy would become how do we do that? Simplify, so we can get this to be 9 over 4y. So it's 1 minus 9 over 4, which is 4 over 4, minus 9 over 4, which is what, 5 over 4? can sort of maybe factor out a quarter. Just get rid of the annoying fractions. How do you integrate that guy?
U equals 9.
Man, just do a substitution. Right? U equals 9y minus 5, you get your du is equal to 9 dy, and so 1/9 du is equal to dy. And so you'll have 1/2 times 1/9. And so this would be u to the 1/2, so you integrate that, you get 3/2 times 2/3. Just 1/27 times 9y minus 5, 3/2. I think I wrote down the answer. Oh, I didn't really simplify, so it was just 1/27 times, that ends up being 4 to the 0/2 minus 4 to the 3/2. The other way would have been nice. Alternatively, we could have just solved for the y. So that'd be x to the 2/3 plus 1. And so we'd end up with y prime is equal to 2/3 x to the minus 1/3. So y prime squared would be 4/9 x to the minus 2/3. And so this means your length would be from 0 to 8. 0 to 8. The radical of 1 plus 4/9 x to the minus 2/3 dx. And how would you integrate that one?
Can you pull out a 1/9?
Sure. I don't know. We don't have a technique to deal with that guy. So if you had tried this, you would have gotten to this point, and hopefully you would know enough to know that we don't know how to do that, and then you go the other way. So that's why it's useful to know that the formula can work with in terms of either variable. And that's kind of it for Arclength. Really, Arclength is just knowing this formula and applying the formula. So most of the work would come with the integration, if ever any work does come from it. So at this point, that's all we need to know about Arclength. We will revisit Arclength when we get to parametric, equate parametric functions, because we have to tweak the formula to deal with that case. But so far, that's all we need to know. So we are going to be moving on to work. That's 5.4. But in general, one thing you have to remember about Calc 2 is that integration is a big deal. One of the main goals of this class is to teach you a bunch of integration techniques so that you know how to integrate stuff. So you should walk away from it being very comfortable with integration. So it seems like Most of the recitation last time, you guys were really focused on working on the integrals. And I don't know, does everyone think they can like recognize like what technique to use if you see a random integral, like you guys are getting that down? Because that's important. Most of your effort should be in just you recognizing the integral. And so if you're having trouble with that, I was thinking about, you know, back when I was in Calc 2, how I was learning, and I actually asked Professor Morrison, and he's like, yeah, I sort of did the same thing. We kind of applied it in different ways, but it was sort of the same idea. Like, with me, I used to like challenge my friends, and later on I used to do it with people I was tutoring. But the basic idea is the following. So you can move to a section where you have all these random integrals where a bunch of different techniques would work. So you don't go to a particular chapter for a particular technique. So you could go to, I forget what the section was, but there's a section in our syllabus that's just about general integration technique, right?
Oh,
so if you look in at the homework problems from that section, right, they're all sorts of random assortments. Like it's no one technique that will work for all of them. You'd have to be able to pick and choose. Oh, based on this integral, I'd have to do this technique, right? And so the idea is you really want to study each technique carefully. And so what you want to do is you want to be able to look at an integral and sort of know what you have to do based on how it looks or what you would need to try. And you can kind of, you want to do this as quickly as possible. So I used to, when I was tutoring people, after I taught them all the integration techniques and taught them what to look for, and then I made them study what to look for, then I would go to this review section or find any other huge list of integration problems, and then I would just start randomly pointing at integrals. What would you do? What would you do? What would you do? And I'd like put a challenge to it. Oh, you have 5 seconds. Okay, so we're down to like the 5-second round. Within 5 seconds, I point at a random integral, and you should be able to tell me how you would do it. So they don't actually compute the integral. They just need to tell me, this is how I would approach it, and this is what I would do. So it's like, oh, I would use substitution here. What would you substitute? Blah, 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 right? Oh, I'm using integration by parts here. What would the parts be, right? And so you kind of do this kind of back and forth. And eventually, like when I was studying, I used to do this myself. I would just go look at integrals and see, could I figure out how to do them? And eventually you get so good at doing this, and the students I used to work with used to get so good at doing this that they could see like 2 or 3 steps ahead. They could tell me, oh, I would do a U sub, but then I would get something that would have integration by parts, and this is what my parts would be. They'd be able to tell me 2 steps into the problem what would happen, right? But it's something you kind of have to practice. And how Professor Morrison said he did it, he used to do I was never into the flashcards thing, I don't know why, but he used to do it with flashcards. He would like write this integral on a flashcard, and on the back, he'd write the solution, you know, that he worked out, and you know, like every couple of weeks he would just flash you these flashcards, and you'd look at the integral, and you'd say how to do it, and then he'd look if he was right. And so you kind of play this game with it, and you know, you eventually you'll get really good at seeing. It will take some time at first, but if you keep doing that, if you keep this practice, keep training your brain how to recognize what to do, the rest is not that bad, right? In theory, the typical Calc 2 student, if they know what to do, they should have the skills to be able to perform it. So if you say, oh, I should do a U sub, in theory you would have the skills to actually do the U sub and finish it. So the hardest part for a lot of people is actually just knowing what do I do now, or when do I do what. And so that's a nice way to do it. And there are a lot of things. There are a lot of things in math that I used to do that with. I mean, I remember back when I was in. Well, technically, it's not high school, because where I'm from, high school starts at 7th grade. Yeah, when we were learning about trig identities and we were doing trigonometry, and we used to have these sets of problems where they would ask us. They would put these equations with these huge, complicated trig. I don't know if you guys ever did that. We have to prove that it's a trig identity, that one side is equal to the other side, and you have to like simplify stuff and like tweak things to make them look the same. And yeah, I used to like challenge my friends who could get there the fastest, who could do that in the least steps possible, because there's no one way to do it. It's just a technique. And you know, you get bonus points if you use really exotic identities, you know, so you get more points for using 1 plus tangent squared equals secant squared than you would for cosine squared plus sine squared equals 1, for example. And you know, you just kind of play these games, or you kind of challenge yourself, and you just kind of know, can I look at something and know what I would do? And that in and of itself is sort of a skill that you kind of have to practice. That's how I would actually go about it, especially if you're having trouble recognizing when you should do what. Because that is a problem that I notice with some students. There are some students where I know skill-wise, they know how to execute something. If I told them do this, they'd be able to go through the steps and do it. The problem is they didn't know what to do in the first place, right? And there are a lot of times where you'll have students that are confused. There are many times I'm grading papers and it would be like, the question asked for one thing, the student did something completely different, but they did it right, and it was a lot harder than what they had to do. So it's like, I know that if they knew what to do, they would have gotten this question right. But it's just that they couldn't see what they were supposed to do. That is something you have to practice. There has to be a segment in your study time devoted to that. You're not just actually going through the problems, you're just looking at it and knowing, this is how I would do it, this is how I would do it, this is how I would do it. And you can get surprisingly a lot out of that. You can do 50 integrals in 10 minutes by doing that. You know, because you're not wasting time writing stuff out and adding in the arithmetic and the algebra. You're just looking at it, you know, oh, I would do it this way. This one I would do this way. This one I would do this way. Eventually you'll be able to get so much experience under your belt by just mentally working through the steps. And yeah, I think that's a good way to go about it. Probably what we can do on Tuesday is that, you know, we can have everyone like write down some integrals that we can solve with the techniques that we've been using, maybe from your homework, maybe from some of the even problems. Everyone just bring in like 5 problems and we'll like put them all in a stack. Like you write them down on flashcards and then I'll just draw a card and we'll spend maybe 10 minutes just going, oh, how would you do this one? How would you do this one? And you'll start to, hopefully you guys, that will be a beneficial exercise. But I was thinking about doing that next week to sort of help you guys out. So we don't have much time to get through this. Maybe I can just sort of explain a little bit about this, like some general concepts that you need to know, and then on Tuesday after we do that integral thing. So do that. Tuesday, April 10th, bring 5 flash cards with 1 integral per card written on them. I'll collect all the flashcards, put them all in a group, randomly pick one, and we'll do a challenge. Maybe I'll give some points, extra points for it, just to make it interesting. Okay, so for extra credit, anyone who can answer this in 5 seconds, I'll give you 1 point on your quiz grade or whatever. You can do some of that for 10 minutes. Yeah. That would be nice. Yeah, so we'll have a challenge. Okay, so obviously, we have to figure out some way. Maybe I should bring the integrals. Because I don't want people to bring in their own integral and just like, answer it after 2 seconds. Yes. Yeah. Maybe I should just gather a bunch of integrals and I'll do the challenge, and then, you know, the people who can get to it the fastest can get some points. Okay. Now we're going to talk about work. I know. God, groan. He did not just do it. Okay. So 5.4, we're going to talk about work. It's a very important concept in physics, for example. It's an application of integrals in physics. So work as a physics concept. It's basically, this is the idea. You have some force acting on an object, and the force can cause this object to move a certain distance. And the work done by the force on the object is defined to be the force times the distance. So this is the force acting on an object. This is the distance the object moves under the force. By the way, that means in the direction of the force. So if I pretend that this desk is 1 meter high, it's probably a little less, and I take a 10-pound object from the floor, put it on the desk, the vertical force would have performed a work of 10 pounds meters. So the units is the force dash length. So example, if your force is in pounds and your length is in feet, then work is in what we call foot-pounds. So it was the length force. Now work is a much broader concept. It's just a measure of an energy exchange between two objects in a system, but we won't really think of it in terms of that definition. We're going strictly with the mathematical definition of work. It's just the force times the distance acting on a certain object. And it does tell you an idea of how much energy is transferred, and so that's why work is something important. It's talking about how energy is being transferred from one object to another, and that's often something very important for us to figure out. We're not going to deal with that situation. We just care mostly about actually computing this idea. And so this equation works nicely when your force is constant, right? So if like for example, the example I just told you about lifting the 10-pound weight off the floor, the force that that object is applying is 10 pounds. It's always going to be 10 pounds. So I'm just going to take 10 times whatever distance I'm moving that. And so you can just do this times that. Now when it gets interesting is when the force itself is actually a variable. That's where the integration comes in. Work, the idea is work is the integral of the force, dx. So this guy here is representing a formula for the force that you can probably write in terms of a distance x. This guy here is representing the distance it's moving. Right? And the idea is, if you look up an interval, and here's a function that describes your force, what you're going to do is on each interval, what you're doing is you're taking the work, you're taking the force times the distance it's traveling, but you're doing it in infinitesimal things and you add them up. And that's where the integral comes from. Okay? So, i.e., if f of x is force acting on object x represents distance moved, then so the work to move from the point x equals a to the point x equals b is given by integral from a to b f of x dx. And this is a much more general interpretation of force. And by the way, if your force is constant, this definition is in fact equivalent to that definition, right? Because if your force is a constant, you can factor it out. The integral of this is going to be x. You plug in b minus a. B minus a is actually the distance between the two. So you just end up with a distance times the constant force. So this is a far better definition of work. And usually that's going to be the interpretation we want to get on it. Now the issue comes in figuring out what is the function we're supposed to be integrating, because that will depend on the situation in which we find ourselves. Okay. So next time we'll go over some situations in Calc 2, which can be able to find functions. These are going to be spring problems where we are going to apply Hooke's law. They're going to be pulling problems and pumping problems. Okay, so we're going to figure out how to find the force in those guys. I'll also talk a little bit more about how the units will help you figure things out and some little nuances with that. So we'll do that on Tuesday after we do our little integration challenge. So start looking over here.
Is there homework, is the Arclength homework due Tuesday?
Arclength, is Arclength on test? No, it's not.
It's on the test.
No. Homework for anything after the test, give me after the test.
So the Friday after?
So that would be Friday.
Thank you.
Did you have a question?
Yeah, no, that's
Oh, yeah. If it's not for the test, don't do the homework. You don't have to do the homework. It'll be nice to look over it if you want the bonus, but you don't have to do it.